Okay, hello everyone. Today our group will talk about explain the operation of the Caesar cipher and the monoalphabetic cipher and discuss methods for cryptanalysis of each. And these are the content of our groups. First is introduction about Caesar cipher, and second is cryptanalysis of Caesar cipher. The third one is monoalphabetic cipher. And the last one is cryptanalysis of monoalphabetic cipher. First, we will talk about introduction of Caesar cipher basics. And what is cryptography? Cryptography is the science of securing communication by transforming information, so only intended recipients can understand it. And the purpose of this is to protect confidentiality, integrity, and authenticity of information. And we have two types of cryptography. These are some examples. The classic one is substitution cipher, and we have modern cryptography, which are AES and RSA. Uh, Next, I will talk about the history of Caesar cipher. Caesar cipher is used in ancient times by Julius Caesar, used it for Roman army message, and it provides basic secrecy before modern computation. And today, the Caesar cipher is not used for real security, but it remains important in the history of cryptography. It is often taught as an introduction to encryption because of its simplicity and because it illustrates the basic idea of keys, encryption, and decryption. Third one, I will talk about the Caesar cipher operation. The first step to do this is we map each letter to an integer. As we know, in the English alphabet we have 26 letters, and we will match those 26 letters from 0 to 25. And the encryption, we will follow the recipe with the key, the shift that we can decide, which is the formula C is P plus K and divide with 26, which P is the numeric value of plain text letter we mapped in the first step. K is shift, an integer, commonly 1 to 25, and we can decide this shift. And C, we have the numeric value of the cipher text letter. And we also have the formula for decryption. And here is an example. As in example, I will choose K, which is 3. And we will encrypt this message hello. As you can see in here, the first letter H, and we map from the first step will be 7, and we plus with the shift, which is 10, and we mod with 26, is still 10. So when we map to the first table, 10 will be K, and we will do the same with the other 4 letters, and in the end the plain text letter hello will convert to KHOOR. So the second part will be the cryptanalysis of Caesar cipher, and I would like to invite Nguyễn Hoàng.
Hello everyone. In this part, we'll cover the cryptanalysis of Caesar cipher. The first part is I will talk about the quickness of Caesar cipher. Caesar cipher only has 25 possible keys, so it's easy to try all by using brute force. Since the alphabet has only 26 letters, there are 25 possible shapes that you can try. This means if someone intercepts a message, they can simply test every possible shift and very quickly to find the original text. For a computer or even a person with patience, this takes almost no time. Because there are only 25 tries, this is instant to break for humans and computer. The second part is that it doesn't discard letter pattern. Frequency of letter E, T, A remain visible. Hardware firewalls are built into network devices, like a root. Meanwhile, software firewalls are installed on an operating system. It is common for a network to have multiple firewalls protecting them. And the next part, I will talk about the method of breaking scissors. The first method is to use brute force. Try all 25 shifts until one makes sense. For example, the ciphertext is KHOOR. If you try the shift 1, which equal to JGNQ, shift 2, IFMMP, and shift 3 to hello, that seems to make sense. Now, the second method is to use frequency analysis. In English, some letters appear much more often than others. For instance, E appears for 12% of the time, T about 9%, and A is about 8%. If you take a long ciphertext and count the frequency of each letter, you can compare it with the accepted English distribution. The letters that occur most often in the ciphertext is probably the encryption of E, and the second most frequent might be T, and so on. By making these substitutions, the message gradually becomes readable, even without trying all keys. And the third part is about the practical details of the cipher. In the original Roman times, only uppercase letters existed, but in modern day, we have both uppercase from A to Z and lowercase. To make the cipher usable today, we usually apply the shift separately to each alphabet. For example, with shift 3 is from A to D, A uppercase to D uppercase, and A to D. This way, if you encrypt hello, the capital H stays capital, and the lowercase letter stays lowercase. For example, from hello to KHOR. Cipher, the second part is non-letters. Cipher is defined only for letters. Numbers, punctuations, and space usually don't change. For example, the plain text hello world will translate to ciphertext with shift 3, KHHOR, ZRGOG. The next topic is about monoalphabetic cipher, and my friend Beck will cover this part.
So I'm going to talk about monoalphabetic cipher. So the first thing about monoalphabetic cipher is that it's a substitution cipher. So instead of shifting letter like a fixed number like Caesar, each letter instead will place by plain text. Text is replaced by some other letter in the alphabet. For example, we can bring A to Q, B to N, C to Z, and D to T, and we do it until all 26 letters are mapped. Second thing we'll talk about is an important property. The first important property is one-to-one mapping. Each plain text letter always map to the same ciphertext letter. The second important property is preserve plain text patterns. Letter frequency, repeated word length, and word shape remain, only the symbol change. And the final important property is no diffusion. Changing one plain text letter affect only one ciphertext symbol, lead to no spreading. Next, we'll talk about key study and example on encryption. So, cipher you only have 25 possible keys, but in monoalphabetic cipher, any up to 26 letters can be mapped to any other letter without repeating. So the number of possible keys would be about 26 factorial, which almost equal 4 times 10 to the power of 26, which is impossible to brute force by hand. For example, we can encrypt the word hello to which H to I, E to T, L to S, and O to G, which will have ciphertext ITSHG. So next we will talk about cipher cryptanalysis of monoalphabetic cipher. So I will let my friend Bazương take it from me.
So we will talk about cryptanalysis of monoalphabetic cipher. First, we will come weakness of monoalphabetic cipher. Even though a monoalphabetic cipher has a huge number of possible keys, about 26 factorial, but it's not secure. Why? Because the cipher preserves the frequency of letter from the plain text. For example, in English, the letter E is the most common, followed by T and A. When we encrypt with a monoalphabetic substitution, the ciphertext will still reflect this distribution, so the most frequent ciphertext letter usually correspond to E. This means that without the key, attacker can exploit statistics to break the cipher. Uh, Next, we will come to brief analysis methods. The most common way to break a monoalphabetic cipher is through frequency analysis. Step 1 is to calculate how often each letter appears in the ciphertext. Then you will compare it with the expected frequency in English. Usually, E is the most common, followed by T and A, O, I, so on. Step 2 is make educated guess about common words like there and or of. Next, you analyze pattern. For example, a double ciphertext letter might map to LL or EE. Suffix like ing or ed can also give strong hint. The process is iterative. You get some mapping, see if Batio plaintext makes sense, then refine your substitution. Modern attackers often automate this with substitution serve or Python scripts that let text possibility much faster. And finally, we come example tools and countermeasure. Let's see a quick example. Take the ciphertext GSRH RSDHVXIVG. Using substitution analysis, we can map it back to ZE secret. With just a few lines of ciphertext, frequency analysis, and pattern recognition makes the cipher vulnerable. Today, tuneless online substitution server or simple Python script can break more alphabetic substitution in seconds. To defend against this, historical improvement include a polyalphabetic cipher like Bayesian or hypomonic substitution which makes frequency analysis harder. However, in modern security, we rely on strong algorithms like AES for semantic encryption and RSA for public key encryption. Monoalphabetic substitution is now mainly used for teaching cryptanalysis and not for real protection. So this is my group presentation. Thank you for listening.